Right. So we're going to start proportional relationships. It's a very important unit. This is going to continue all through high school. We spend a good chunk of our 8th grade year on linear relationships. And so this is like the precursor into linear relationships. Okay? Basically what you have is, let me pause. Okay. So for proportional relationships, okay, the biggest thing is that they go through the through the origin. So they go through 0, 0. So if they give you a table, you can look for 0, 0. If they give you a graph, you're going to look that it goes through the origin. And then the equation looks like this. There's no plus on the end because it goes through the origin. It doesn't go through any other point.
I have a question. Why do you put parentheses for the graph thing?
That's a point on a graph.
Okay.
So yeah, it's always x, comma, y. That's not going to go anywhere. It'll always be that way. All right. The biggest thing with this is you're going to hear a lot proportionality, and you're probably thinking, hey, we did proportions, right? And they looked like this. This is a different type of proportion. Okay, we're still going to be comparing y over x, but it's just going to look a little different. It's still a ratio. And when you hear me say constant, okay, this is spelled with S-E, but I want you to think of it like a K. Because when we find constant of proportionality is represented by the letter K. So constant, anytime it's asking for the constant of proportionality, it's looking for K. Well, what is K? K is when you take y and divide it by x, whatever number that may be. Yeah, it's pretty easy. And what makes these different from these, okay, is that they are constantly the same. So if you do y divided by x and get 2, if you do it again, you'll still get 2, and you do it again, you'll still get 2. These kind of lines, they change. It's different because it doesn't go through the origin, right? It's not a perfect line. They're a little off. So these are kind of what we want to think of as perfect. They do the same. They're constantly the same all the time, right? Because if you do 12, if this is your y and this is your x, 12 divided by 1 is what?
12 divided by 1 is
12. 24 divided by 2 is what? 12. And then the next one would be 36 divided by 3, which would be 12. So notice how that's constantly the same? That means it's proportional. It's a constant of proportionality. Right? What does it change? How much is it changing? So like this one has a ratio of 1 to 12, because that's what we got every time. Didn't we see ratios when we did proportions? Yeah, and we had to set them up on top of each other. So I done this one like 1, or would have been the other way around, sorry. 12 to 1, right? All right. Proportional relationships is y over x, right? So it looks like this, y over x, which just means y divided by x. And we call that the constant. Of okay, but remember I told you to think of constant with a
Okay.
K, yeah.
I don't know why, but proportionality seems like the longest word.
It is a very long word. So you're going to hear me ask a lot, hey, what's the constant? What's the constant? Or another word is rate of change. When it's in this form, we call it slope. It's all the same thing. Constant, proportionality, rate of change, slope, they're all basically the same thing. Just a bunch of names for the same stuff. Which is probably what makes it most confusing for people. All right. So I already told you the constant is the value once you divide. So like up here, we did 12 divided by 1 and got 12. 24 divided by 2 and got 12. 36 divided by 3 and got 12. So the K for this one is and then the equation looks like this. I've already put it over here for you. Be on your reference sheet as well. Okay, and then we have X and Y, which is on a graph. All right, so X is over here on the sides, and Y is the one that goes, yeah, up and down, right?
So last X like this.
Now here's something that is kind of, X is what we call, that means he can stand on his own.
Does a Y look like this? Yeah, but naturally. Okay.
I don't know.
Like this? It's okay, that's just a Home Depot ad.
So basically the independent variable, that means like when you go to like a concession stand, right? A candy bar costs $2. The candy bar will always cost $2. But what's going to change is your total, depending on how many candy bars you buy, right? So Y is the one that we call dependent. It depends on the other one to tell us what it's going to be. So if I go to a concession stand and I get one candy bar, it's $2. So it'll still be $2 here, and my total will be $2. What if I get 2 candy bars?
$4.
Yeah, each candy bar still costs $2, but it's going to change my total to $4 now. And what if I buy 6 candy bars? They're still going to cost $2, but what's my total? $12. So the y changes based on whatever x is telling us to do. Because this is multiplying, right?
I have a question.
Yeah.
What about tax?
It doesn't have to do with this. I'm giving you an example, a real life example.
Yeah.
What about that?
At how something can change something else. Okay, you could, let's think. All right. So if they give you a table, you have to find the ratio, or K, the constant of proportionality, by doing y divided by x. So we need to see if they're the same. Okay, 6 divided by 1?
6.
So it would just be like this, or 6. 12 divided by 2? Still 6. 18 divided by 3? By 4? 6. So all of these are the same, which means the constant of proportionality is 6. Okay, if this was not proportional, they wouldn't all be 6. Okay, you would see a change. So like this one would be 6, maybe this one's 7, maybe this one is 9. It would just be different every time. That's how we know it's proportional, because every time we do y divided by x, no matter which one we pick, it's all the same. It's all constant. See how that word works? It's constantly 6. Okay, this one, 2 divided by 10, 5. Or 2 divided by 10, 10 divided by 2, 5. 15 divided by 3, 20 divided by 4, 5. 25 divided by 5, 5. So it's all the same. So our constant of proportionality is 5. 4 divided by 8. 0.5, yep. Or you could do it as a fraction. You could just simplify it to 1/2. That works too. Or you could do 0.5. Both would be acceptable. 6 divided by 12. 1/2. 7 divided by 14, same thing. So 1/2, or you could say 0.5. Both are acceptable. But again, it's the same, right? It's a half every time.
Yeah, that confuses me when I look at it.
Yeah, they're both the same. All right, so when they give you a word problem, you just have to read. We know that we're going to do y over x, right? So we have to read and figure out what they are. Proportionality that relates to y. Y is the cost. And x is the number of pounds. So this is your money. If you want, you can label it. So what was the cost? 23.28. And how many pounds? 6. Good. All right. So 6 goes into 2, 0 times. 6 goes into 23. How many times?
8. No, 3.
3. I'm going to do this up here. I don't have enough room. Six goes into 52. 8, right? 48. Six goes into 48, which makes happy 0. So 3.88 is my K. And then once we have these, what they do with it is they put this number into this equation up here, right? So if I was to write this equation, it would look like this. Y equals 3.88, and then we just put X, like that. And what would this equation look like? Y equals 6x. Good. And this one would be 5x. And this one would be 1/2 x. Or 0.5x. Exactly. So that's why we have to find this K so we can use this equation. It helps us. All right, number 5, again, Y is the total number of miles. So, miles. X is the total number of hours. So, 220 miles and 4 hours. Should be 55. 220 divided by 4 is 55. So Y equals, we take the K, which is 55. So 55x. Perfect. Basically, yeah. All right. So here's some different things. First, let's look at the graphs. Are these both proportional? Do they both go from the origin? Do they start at the origin?
Yes.
Yeah, they do. So they're proportional. So I should be able to find K for these and have no difference. Okay. How do we fill in the chart? Well, they've given us some points, so we can start filling them in. This origin here is going to be 0, 0. If I divide those, is that going to help me? No. So would it be a good idea to put that one on my table? Probably not. It's probably a better idea to use these. Because 0, 0 is not going to help me find K. So the first one, this is why we practiced graphing yesterday. The first one is at 1, and the Y is 10. Very good. And what's the second one?
22.
X always comes first. 2 and 20.
I have a feeling it's gonna go like that.
Seems like it's constant, so it should be the same. So the next one should be 3 and 30. Good. And we can check the graph. 3 and
30.
see how it's kind of predictable. And then 4 and 40.
Good job, Isaiah.
Okay, then you're going to find your K. You can pick any of these to check. 10 divided by 1 is 10. 20 divided by 2 is 10. 30 divided by 3 is 10. 40 divided by 4 is 10. Exactly. So no matter which one you get, you should get the same number. If you get different numbers, it's not proportional. Okay, and we'll look at those, like I said, later, they'll have you look at them. But you'll keep hearing me remind you.
You have to repeat.
Okay, graphs and tables are not just a bunch of numbers. They represent data. They represent stuff that's important, right? So X isn't just X. What does X represent? Number of tickets. Okay, so if X is 1, how many tickets are we talking about? 1, because X is 1. So at 1 ticket, what does that K even mean? You have to interpret it. What does it mean? It's not just 10. What does it mean? What's $10? 1 ticket. There you go. 1 ticket cost $10. That's what that means. And you can tell that by the label on your graph. Okay. Number 7. We don't have any dots, but we can find our own. And you'll have some like this on your homework, so I want to make sure I'm clear.
2 and 6.
Yeah, make sure you pick something at a perfect crossing. Okay? So any of these where it crosses at, do you see how these meet right here? That's what you're looking at. Ones that cross at a perfect meeting point. So you can use any of these points. You don't want to use like this, right? Because we don't really know where that is. But when they meet at a cross, it's going to be a perfect number. So 1 and 3. This one's 2 and 6. This one is 9 and 3, right? It's perfect. We don't have any like 1.5s. That's just too much, right? Let's make it easy on ourselves and pick perfect points. Following the pattern, what do you think the next one will be? 4 and 12. Good. Yeah. 9 divided by 3, 3. So K is 3. Oops. Now what does that 3 actually represent? X is 1. Right. 1 hour, 3 miles were walked. Or you've also seen like, it could be written like this, 3 per hour. Very good. What about the equations? What would the equations look like for this one? Oops. Y equals what?
3x.
The first one.
Oh, 3x.
X. Good. And then this one would be, because there will be some where they're going to give you the equation and say, what's K? Well, that's really easy, right? When they give you the equation, it's really easy to find out what K is. It's already done the work for me. All right. Is the number of calories proportional? I want to know, okay, is it constant? All right. Is the K the same? Here. Just a fancy way for saying, is it constant? So when you divide y divided by x, y divided by x, you should get the same number. So 117 divided by 1 is going to be 117. Okay, I'm going to show you this one.
Oh, I think I had it in my head.
234 divided by 2 is what?
13.
Do not trust the first two numbers. You need to check them all because they love to be tricky. For our notes, there's not any tricky ones here, right? But the people that make those questions, you know what they're trying to do. So always check them all. Don't trust
That one's right.
that the first two are the same. Oh, it's done, it's constant. Because they'll make the very last one be different, just to be turkeys.
Like the star test people.
Yes, they will do that just to try to trick you. So if you're doing this on an actual test and stuff, always check them all. For this, for us, is it all constantly the same?
Yeah.
Yes. So it has a constant change of 117 each time. Because that's what we're figuring out. We're just figuring out how much it's changing each time. How much the graph is growing, how much the table is growing each time. So what is the constant? Well, remember that's just a fancy word for the K. The K is 117. And then it wants us to write the equation. Well, we've already kind of been practicing that, so what would it look like?
Y equals 117.
Okay, and just kind of a little example of, well, what is the whole point of doing this, Miss Daly? Well, once you have an equation like this, you can solve anything, right? What if they wanted to know how many calories they were going to burn if they went 200 miles? We would just plug it into the equation. So once we have this guy, we can solve all sorts of things. For example, what about if Keith ran 7 miles? How many calories would he burn? So we have to figure it out. Just double check. What is miles? Miles is the X. Calories is the Y. So if they say 7 miles, you're going to put the 7 in place of the X. So we set up the same formula. Right? And then instead of X, we're going to do parentheses 7. Because in miles, well, he would burn 819 calories. You can also go the other way. This time they gave us calories. Well, we're still going to use the same formula. So our equation, we're going to write that down. But 1,170 calories. Calories goes for what letter? X or Y?
Y.
Y. So I'm going to erase the Y. We're going to put that number in its place. And earlier, Isaiah, you said this looks like a one-step equation, and it is. That's how we're going to solve it. So I divide both sides by?
It's just 10.
Yeah, 117, which means 10 miles. So he would have to run 10 miles to burn 1,170 calories.
It's crazy. You can eat that in one meal.
Yeah.
It's from 10 miles to burn it all away.
So this is why we find these equations, so we can solve problems or answer questions. Right? That one equation helped us answer 2 different scenarios.
Why is there
These many foods have a lot